All right. Good afternoon. Happy St. Patrick's Day. Just kind of a fun excuse to rain, I guess. I have an erratum from last day, and it was one of those where you're like half asleep, and then you kind of wake up, and I realized that I said the wrong thing. I called it the wrong thing, so I have to fix that, of course. I make mistakes, and you know what? To punish myself, I'm going to write it in red. Erratum. I had to look up errata. I thought errata was it, but errata is plural, and luckily there was only one mistake that I made, so it's erratum. It's the fun fact. I said the RMSE, that one was fine, is the root mean squared error, and now I have to check my notes. I realized the problem was I didn't write it in my notes. Felt wrong when I wrote it. I just went for it anyways. And maybe I'll put it down. Is in fact the root mean squared error. But then, the RSE, this is where I really stepped in it. I just called it the root squared error, which is sort of true, but it is the residual standard error. So I'll write out what I said it was, the root squared error. That's wrong. It should be the residual standard error. That's okay. Usually we don't even, we just use the acronyms. And remember, the residual standard error is when we're penalized for having too many predictors in our model, right? Or it takes into account the degrees of freedom as opposed to just the sample size. So as long as you keep track of that, then like me, you're allowed to slip up every now and then, I guess. So there, fixed it. Not a huge deal. Okay, so picking up where we left off, right? So last day we established model assessment metrics, right? And so we spent a lot of time talking about them, so I don't really want to review them because we've got a lot to cover today. And so last day we established some common model assessment metrics, right? How well does our model fit our data, right? Common model assessment metrics, right? Asking things like, how well does our model fit the data? Okay. So we talked about the RMSE and the RSE, the residual standard error. Did you guys ever hear about, I'm not sure Netflix is doing it anymore. I think their algorithm is top notch. But back in the day when Netflix was sending out DVDs still, they had this contest, and you could win $1 million if your model predicted better than their current model, right? And I'm pretty sure that how they gauged it was by the RMSE. So if you had a significantly improved root mean squared error than their current model, then you would win. And of course, against all the other competitors, then you would win that $1 million for that year. And then they would apply that algorithm and so on. Right. And so kind of a fun thing to think about. I think those days are over. But I don't, yeah. Anyways. The root mean squared error is used across the board. So it is everywhere. And so because we're always building models, right? And so all these models are going to have residuals. And so it will always have the root mean squared error. Yeah, so it'll be everywhere. Okay, and as a side note, I don't know if you guys have checked out Kaggle. Kaggle is kind of along the lines of the Netflix competition, not as big, but there's some fun projects that you could look at doing and kind of joining competitions. And some of them have a significant amount of monies involved. So just as a little side note, if you haven't checked out Kaggle, Kaggle posts various modeling competitions or predictive competitions, posts modeling / prediction competitions. That seems weird. So if nothing else, it's kind of just fun to poke around there and see what's available, right? And so, and maybe I should clarify, because in case you don't know what I mean when I say Kaggle, right? So you can just search Kaggle and you can look there and you can register for competitions and you can work in groups and you could potentially win some monies. So there's tons of money in predicting and building models, but of course we need to know how to assess our models, and so that's what we talked about last day. RMSE, of course, is the big one. The residual standard error, I'm trying to say it so it sticks. The R squared, the AIC, the BIC, Mallows CP. So you'd have to do research and figure out which one is the best in your situation. But across the board, the RMSE is kind of widely the model assessment that we use. Okay, so especially if you are going into a competition, you don't want to just look at the root mean squared error of one sample and just say, oh, my model did so well. It works amazing for this one sample, right? You want to be really sure that you have this robust model. Okay, and so instead of just checking and assessing the model with the sample that we built it on, right, then we do cross-validation. Okay, so we need to remember that we built our model using sample data, right? And so using the sample data to assess our model is it's a little bit, I want to say, icky, right? It's a little bit weird, right? Because it's going to perform the best on the sample because that's what it was built off of, right? And so we need to remember, and maybe so I'm not going to do any review here. So I'm going to add a little end of review twiddle thing. But we need to remember that our model was built using our sample, right? We need to remember that our model was built using our sample. Okay, so that means it's going to perform the best on our sample, right? And so to get an accurate model assessment, what we need to do is ideally, we need to build our model on a separate sample and then test it against some other data, right? So to properly assess our model, we should apply it to what we call a holdout set. Okay, so to properly assess our model, we should use cross-validation. Cross-validation. This cross-validation is not really possible if you have a very, very small sample, although there are ways to get around it. But cross-validation, there's lots of different ways that we can do it, but at its root, we separate our sample into a holdout set and a training set. Split the sample into a holdout set and this is probably not unfamiliar to you. A holdout set and a training set. You build the model on the training set, and the training set is going to be quite a bit larger than the holdout set. Training set will be larger than the holdout, right? Because you want to build a model using as much information as you can, right? And so the training set will be larger than the holdout set. And so then, and maybe I'll call this kind of step one. Step two is to build the model using the training set. So build the model on the training set, right? It's the training set because you're training your model, okay? Then you assess the model on the holdout set, right? So how well does this model do when it's applied to kind of foreign data it hasn't been built on, right? You want to randomly select your holdout set, but then you build your model on your training set and then assess the model on the holdout set. Okay. So that's the general idea of cross-validation. And sometimes if you have a huge sample size, then you can do things like you can have the test set or the holdout set, and then you can have, I can't remember what the middle set, but then, so you build, sorry, let me start over. You have your training set, you train your data on your training set, then you apply it to a 2 out of 3 subset, which is where you pick your model, and then you apply that model to your test set. So a little bit more involved. It requires lots of data, of course, but usually cross-validation like this is enough. Okay, and so, and I can't remember what the middle subset is called, but that's okay. So this is all good, right? You're not assessing your model how it performs exactly on your data. You are assessing it based off of some subset that it hasn't seen before. But even better, right, is if you do this multiple times and then look at the average model assessment, right? And so when I say model assessment, that's maybe the root mean squared error, or maybe it's the RSE, or maybe it's the R squared, or maybe it's the AIC, right? Depending on what you have chosen to look at. right? The BIC, Mallow CP, the list goes on and on and on and on. Right? Usually RMSE is the one to look out for. Okay, so and then ideally we do this many times and consider an average model assessment or an average of the model assessment, and consider, doesn't have to be the average, it just is often the average. Can't write consider today. Consider, I keep doing that weird thing. Ideally, we do this many times and consider the average of the model assessments. Right, when we do this many times, we can, one of the ways that we can do that is using k-fold validation. And so we can use k-fold cross-validation, which is a one kind that we could use. And so instead of just one cross-validation, you're going to do k of them. So you split your sample into k subsets, and then for each iteration, you're going to consider one of those subsets as the holdout set. Okay. And so you split your sample into k subsets. Okay. And then at each iteration, and of course you randomly split your sample into k subsets, right? And then at each iteration, use a different subset as the holdout set. Use a different subset as the holdout set. And of course, the remaining subsets, right, all except for that one subset that you've pulled out, the remaining subsets are, of course, going to be your training set. But that should be. Oh, in this case, the K is just a placeholder. So it's just a variable, but it's so K, you can do 3 subsets. So that would be a 3-fold cross-validation. So it's just the number of subsets. Yeah. And then K means is something different. Yeah, it's a different, I'm sure at some point in the theory, they merge and the K's are related somehow. I have no idea how though. Okay. K. Let's see here. Good. All right. So we've established how we're going to assess our model. So that's good. That's an important part, but we haven't actually talked about how we're going to build our model, right? How do I pick what predictors go into my model, right? And so now we have, or we now know how to assess our model. But we haven't actually built a model yet, right? Or we haven't, but we haven't looked at how we build models, but we haven't looked at how we build models, right? So now what I want to do is look at, okay, what are some of the ways that I could build these models? How do I arrive at the best model? And this is where people get kind of uncomfortable, and myself included, right? Because there's no, besides the model assessment techniques that we have, right? So besides looking at the RMSE, looking at the R-squared, looking at the AIC, right, and knowing what I want, right? I want to minimize my AIC, I want to maximize my R-squared, right? And maybe there's a trade-off that I need to make, right? But picking the best model is the reason we have jobs, right? Because there is no set way of building the best model. It's going to be it's an art, right? Is looking at your predictors and knowing how to figure out what the best model is, right? And how it's going to work consistently at predicting new values, right? And so that's our goal. And I think it's really helpful if you approach it like an art rather than a hard science where, okay, and then I do this, and then I do this, and then I do this. You're going to need to kind of float around. I kind of imagine it like you float around in the predictors and you say, okay, I have a pretty good idea of which ones I want in here, but let's look at a couple of different ways that I could arrange these and see how they perform in my model, right? Or rather, how they make my model perform. Okay, and so in a data set, we will have a certain number of predictors, right? So a certain number of features, they're called, or not outcomes, explanatory variables is the word I'm looking for. So in a data set, we will have a number of predictors, features / explanatory variables that could be included in our model. That could, that could be included in our model. Okay, but I want to highlight or underline the could, right? Because they could be in our model, but let's always remember that you want the simplest model possible, the simplest model that performs the best, consistently the best. Okay, so you're going to have a number of explanatory variables to choose from. So what are some of the ways that we could pick predictors, right, to be included in our model? Well, one of the ways is to look at the p-values of each individual one, right? And so there are many ways to decide on a model, right? To decide which predictors should be in our model. The first one is usually not an option, right? If you have a large number of predictors, imagine trying to find all the possible subsets, right? And so it's not really an option, but technically it is. You could consider all possible subsets, right? So if you have A, B, C, and D, or maybe let's just look at A, B, and C. If you only have 3 predictors, now we know you usually have more than that, right? That would be weird to only have 3, but A, B, C. So I could look at A, individually. Then I could look at B individually, and then I could look at C individually. So then I have 3 models already. Then I could look at A and B. Then I could look at A and C. Then I could look at B and C. So now I have 6 models. And then I could look at A and B. Then I could look at A and C. This gets crazy, right? And so because I can multiply them as well. So the all possible subsets, yeah, you need a table or a computer to do it. A computer will do it. It just is going to take it a long time. You can see how it would take a long time, even with just 3. Now, when I say long, I mean like a second for three predictors. But what if you have 30 predictors, right? Then it's going to take a long time. So you don't want to waste your time with that. We have other methods that we could do it. But I will say all possible subsets is computationally expensive, right? So usually we don't do that because it's computationally expensive, right? But if you wanted to be really sure and you only had a certain number or a small number of predictors, then you could do it, right? But what you'll see is that the list of options kind of goes on and on and on. So even with 2 predictors, it gets a little out of hand. So the second option is, and maybe I'll call this the 0th option because it's not something that we're going to do. So I'm going to change this to 0, 1, 2, and 3 because there's kind of 3 main players. Okay, and so so each predictor, once we run the model, is going to have some p-value associated with it, right? So to tell us if it's significantly contributing to the model or not. Okay, and so one of the ways that we could do it is forward selection. You can start with nothing in your model and then add predictors incrementally, right? Until you reach a point where it doesn't become significant anymore. Okay, and so forward selection is one of those options. Start with a model with just the intercept, right? So we call that a constant model because it's just the intercept, it's just a straight line. So start with the intercept as your model, which is really no predictors. Then at each iteration, add a predictor until predictors are no longer significant, right? Significantly contributing towards the model. Then incrementally add predictors until they no longer add significantly to the model, until they, I'll change that to until they are no longer contributing significantly to the model, contributing significantly to the model. Okay, that's one way to do it. The other way to do it is the opposite way. What if you throw all your predictors in there, right? And then slowly pick away the predictors that aren't contributing. Okay, so that's going to be called backward selection. So you start with a model with all the predictors in there, and then incrementally remove the least significant predictors from the model. Okay, so backward selection, I'll use the same format here. Start with all possible predictors in the model. Yeah. Then incrementally remove the predictors that are contributing the least, so have the highest p-value from the model, and then rerun the model and see what happens. Now, of course, R just does this and Python just does this. And so you don't have to do it, but you have to know what it's doing, right? Otherwise, you can't talk about it, and that's your job to talk about it. So, so start with all possible predictors in the model, then incrementally, oops. Remove the least significant predictor, which is really the same as saying the predictor with the highest p-value. Okay, so you're removing the least significant predictor. Of course, you want to pluck it out because it's not contributing. Technically, you should move it to the end of the list, but of course, R does that in the background. So it's not something that you're going to do by hand, so you don't have to keep track of that, but there are kind of technicalities in there. So you start with all your possible predictors, and then you find the least significant one, pull it out of the model, okay, rerun the model. What you'll find is that every time that you rerun the model, those p-values are going to change, right? So you can't just take away all the least significant ones and then rerun the model, because it's not going to give the same results, okay? And so typically, so one thing to note, the p-values will change depending on what predictors are in the model. Change depending on what predictors are in the model. I kind of think of it as a group of people that are carrying something heavy, right? And so your model is trying to figure out what's going on in your data. So it's kind of trying to carry something heavy. And then, so if you have someone that's really strong in your group, then of course they carry most of the weight, right? Because everyone's kind of like, oh, you've got it, right? Yeah. But then if that kind of strong person leaves, then everyone else kind of has to carry more weight, right? And so the p-values behave the same way, where they're like, oh, that important predictor left, okay, we got to pick up the slack here, right? And try to model this outcome. So it's the same kind of idea, at least that helps me think about it, and helps me remember that those p-values are going to change. Okay. And so I didn't finish this thought here. Well, I did, but start with all possible predictors in the model, then incrementally remove the least significant predictor until all predictors are significant. Until all predictors are significant. And just as a side note, of course, I think I've said it a couple of times, right? When I say significant, what we mean is we mean statistically significant. Significant is statistically significant which is the p-value less than the alpha level, right? And it depends on what you use as your alpha level, but usually it's 0.05, right? And once you have a look at some linear model output, which we've already seen, but we didn't really look at the significance, the p-values yet. But once we have a look at that, what you'll see is that there's little stars to show you at what significance level it's significant at. So it does a lot of the work for you. Okay. Okay, so good options, right? Start with nothing and then incrementally add things, add predictors into our model until they're not contributing anymore. Or start with all of them and trim it down until you have a model where everything is contributing to the prediction, or do a mashup of the two, right? So you could, the stepwise selection, or stepwise regression. Now let me just see here. Sometimes it's called, and in my notes, sorry, I have backward elimination. Because it's slashing predictors as you go, right? And so it's forward selection, backward elimination, although it makes more sense than selection, I guess, but you could say selection. And then finally, stepwise regression is, of course, a combination of the two. Oops. Is where, and I'm pretty sure it starts with forward selection. And then as you add predictors, you also eliminate, and I have to confirm, but I'm pretty sure the stepwise regression starts with forward elimination. But I've already had to issue one erratum, so I'm gonna go for it. I'll check. I guess, where is it? Maybe it doesn't say. They sneak around it too, I think. Okay, start with forward selection. There it is. I've confirmed it. So start with a constant model, right? Which is with the intercept as the model, okay? And so, which is the same as forward selection. Forward selection. Then if a predictor is added that doesn't contribute to the model, or if you add a predictor that makes other predictors not significant anymore, that can happen, right? You brought that, so that strong person came back and from their lunch break, and now they're picking up the slack again, right? That's that new predictor that you added in. So then maybe the other ones are not significant anymore, right? And so then you could eliminate those, right? And so start with a constant model and incrementally add predictors. And remove any non-significant predictors. And remove any non-significant predictors, which is backward elimination. As they appear. Right? So it depends on what predictors are in there already. So of course there's kind of ifs and buts, but Oh yeah, so each predictor is going to have a p-value in the LM, in the summary of the LM output, and so that's how you're going to choose if it's significant or not. And we've got it worked out in the labs, so so you'll see it. It's hard for me to show on here because our Studio Cloud is so slow. Okay, but we'll see it. Okay, so of course, R implements these just automatically, or not automatically. Maybe I should change this to use R to implement these. Use R, rewrite it, to implement these. Right, there's built-in functions. Use built-in functions in R to implement these. There, right? What I'm saying is don't go and do this by hand. That would be crazy, especially if you have like 20 predictors or something. And one thing to note is that as a rule, so for good data collection, your data set is always a lot larger. So your sample size is always going to have to be a lot larger than the number of predictors, right? It's just, it's sloppy to have a huge number of predictors on a small sample size. And so your sample size should always be a lot bigger than the number of predictors. So just as a quick note here, your sample size, because we saw that sometimes, you know, in theory, we should have, we have n minus p minus 1 degrees of freedom, but if I have a large number of p compared to n, then that can go to 0 and it makes a mess. But I just want to re-emphasize here that your sample size should be much larger than the number of predictors. Kind of out of nowhere here, but it was on my mind. Okay. So we can use these different methods to arrive at usually different models. So depending on what method we use, we might arrive at different models. And then you could compare those models using the assessment techniques or the assessment metrics that we use established. Right, so often these different methods of choosing predictors, these different methods of choosing predictors yield different models which we can compare using the model assessment metrics, right? Using the model assessment metrics, right? The RMSE, R squared, AIC, etc. Lots of options, and you might have to declare ahead of time which one you're going to use, right? Otherwise, you might have a favorite model, but also simplicity wins out too, right? If you have a simple model that does roughly the same as a more expensive model, then you should pick the simpler model. Oh yeah, the AIC is what we ended on last day. It's a Keki's information criterion, and it's another measurement that we could look at. Okay, so what are some of the things that we could do? We could also consider a weighted regression. So for things like, if you know that some measurements have less variability, they were more rigorous than some other measurements, then you might want to look at a weighted regression. So then you can assign weights to your observations. For example, if you're doing a study, maybe a study on weight loss, and initially, you're coming and you're having everyone come to the clinic to be weighed every day or whatever, then you're using the same scale and everyone's coming in and you are recording those values, right? Whereas maybe after 2 weeks, you let everyone self-report from home, then all of a sudden you have these weights that are coming in, so you are getting that data, right? But all of a sudden, people have different scales. People might not be reading it properly or waiting for it to set properly, or I don't know, all these things that could go wrong, right? So we have these two different sets of variability, right? And so we can use a weighted regression. Okay. We can use a weighted regression to account for maybe different number of observations, right? So maybe you have one person in your study who's reporting values twice a day and everyone else is reporting only once a day, and stuff like that. You want to use that data, but also you want to kind of weigh it down a little bit, right? Because you have more of those observations. And so you can use a weighted regression to account for different number of observations per subject, or different precision. In the measurements. The example in the textbook looks at real estate data. So of course, a home can be sold multiple times, right? But the sale price from 2003 is not going to be as relevant as the sale price in 2013, right? So then you would weigh that down a little bit. You want to keep it in there because it's contributing, right? But you want to kind of weigh it down because it's not as relevant as the new sale prices. Right? So a couple of different ways that you could look at it. One thing that is a little bit confusing is that we can build confidence intervals. We can build confidence intervals for each of the coefficients, okay? But also prediction intervals, which are different. The prediction intervals is for one predicted value. Okay, so a prediction interval is for one value, whereas a confidence interval is for the coefficient, right? The coefficient is a statistic, right? So something that I've calculated from a sample, so it's based off of many observations. And so then I can build this confidence interval. But then if I'm looking at one predicted value, then I can build what we call a prediction interval, which is the same, but because it's only for one value, it's going to be quite a bit wider. Okay, so we can build, and I'm kind of skipping one thing, but that's okay. We can build confidence intervals for each of the coefficients. And of course, the built-in output, it can give you the confidence intervals if you ask for it for each of the coefficients. it uses the standard formula approach, but you could also use a resampling approach for each of the coefficients if you wanted to build a confidence interval. You'll find that they're very similar. So we can build confidence intervals for each of the coefficients. Okay. Or I guess not or, it's not one or the other, you can do both. But we can also build an interval around one predicted value. We can also build an interval around a single predicted value. Which we call, which is a prediction interval. This is a prediction interval. Okay. For a single predicted value. Okay. Those are just kind of, you can do weighted regression, you can build confidence intervals, you can use prediction intervals, but of course, those are just things to keep in mind until we actually see some. But just keep in mind the difference between a confidence interval. A confidence interval is based off of a sample, whereas this is for a single value, right? So here, the confidence interval is based on sample information versus a single value right down here. Okay, so that's the difference between the two, and often the prediction interval is going to be a lot wider than the confidence interval, but we'll see that. Okay. You probably, because many of you are in my 300s, and so you have probably dealt with some dummy variables or some categorical variables. And so far we've only looked at really numerical predictors. What if we have categorical predictors? The number one thing that we usually do is we, why would you need a confidence interval? So each coefficient, right, is just an estimate based off of the sample, right? And so that coefficient would change depending on the sample. But if you wanted to know kind of the plausible values of those coefficients, then that would be a confidence interval, right? You would build a 95% confidence interval around each of the coefficients. And if the interval is quite small, then you know that you have a good prediction, right? It relies on the standard error. So if you have a small standard error, then your confidence intervals can be small as well, right? So there's lots of different things that you could look at there. But it's really just to build an interval of values for your coefficients, not just the one from your sample. Good. So what if we have categorical predictors? Right, we can convert them all to dummy variables. Dummy variables are 0, 1 variables. So we typically convert categorical data into dummy variables. Which is 0, 1 data. Oh, keep doing that. 0, 1 data. right? Which means that you create a predictor for each category, right? Create a predictor, oops, for each category, right? Then you're going to have a series of on-off switches, right, for each predictor to indicate which category it's in. Now, what happens if I have a large number of categories, right? So then we might think about, okay, I'm not going to gain a ton of information from being really nitty-gritty in these categories. Can I consolidate these categories? So if we have many factor levels, they're called, right? Or many categories, many factor levels, which are categories. We usually try to consolidate into fewer categories, right? We usually, try to consolidate into fewer categories. And it depends on how your data was recorded, right? Usually if we have, and we use P again, which is kind of confusing, but if we have P categories, or factor levels, we usually only create P-1 dummy variables. We usually only create P-1 dummy variables, since the last one would be if all of them are off, right? Since the last one would be when all others are off. Or 0. Okay. The only time that we would use all P dummy variables is in machine learning, where we want to have all of them explicitly, and that's when we call it a one hot encoder, right? So a one hot encoder, so versus a one hot encoder includes all P dummy variables. Which is used in machine learning, apparently. I don't know. I don't know anything about machine learning yet. Maybe I'll have to teach it one day. Then I'll learn it. So a one hot encoder includes all P dummy variables, which is used in machine learning. For example. Okay. So it's the only difference. Okay. All right. The special case of ordered factor variables, you can sometimes just convert them to numerical values and then use that as a numerical variable. And so a special case is when we have ordered factors, which we've called ordinal data right before. There's some natural ordering. Ordinal variable. So when we have ordered factors, we could assign each value or each category to a number. We could assign a numerical value to each factor level, then use that as a numerical variable in our model. Then use that as a numerical variable in our model. So that's kind of cool, right? Because then you've captured that ordering, right? Small numbers are going to have the first order, and then the large numbers are going to have the largest order, right? And so you've been able to capture that with just a numerical variable, right? So a lot of the time, one of the problems, and not necessarily a problem, but one of the things that we've seen already is, or that I've said already, is that depending on what predictors are in the model, right, that's going to change the p-values, right? So that strong person that comes in and helps carry the model, and then that's a strong predictor. And so then the other ones are kind of slacking off. And then, so then they're not contributing to the model so much. But then that strong predictor leaves, and then everyone has to pick up the slack, right? And so what we're noticing here is that the predictors kind of rely on each other, right? They're dependent on each other, okay? And so we will notice that predictor variables, right, are often correlated, right? And you've probably heard that that's a bad thing. And I think we talked a little bit about multicollinearity, but it is something that's going to happen, and it is something for us to keep an eye out for, right? So it's not necessarily a bad thing if they're just correlated, whereas multicollinearity is a bad thing. Okay, so we will notice that predictor variables are often correlated, right? So here I just want to add in kind of a subnote, I guess, right? The p-values will change depending on what predictors are in the model. So the p-values will change depending on the predictors included in the model. Right, so that's what we're going to notice. They're often correlated, which may affect the coefficients as well, right? And so not just the p-values, but also the coefficients. So which may affect the coefficients in the model. And that's when it might be good to consider the confidence intervals, right? Did the confidence intervals for each coefficient, did they change a lot when I altered the predictors that were in there, or did they stay kind of the same? Okay, so that's just something to keep in mind. Okay, and so it's going to affect not just the p-values, but the coefficients, and everything in the model is going to depend on what predictors are in there. Okay, and so one of the extreme cases of this is if we have multicollinearity. So the extreme case of this is if if we have predictors, and I'll add two or more predictors. Make room here. 2 or more predictors that are exactly correlated, right? That have a correlation of 1. Meaning if I have, if I include maybe what if a model includes my hourly salary, but also my yearly salary? They're the same, right? And so I have this redundant piece of information, and it's going to take over my entire model, and it's not going to work. And usually R will tell you, hey, there's multicollinearity here. What do you want me to do about it? You have to fix this. I can't do this. So dramatic. So the extreme case of this is if we have 2 or more predictors that are exactly correlated. Are exactly correlated, right? This is what we call, this is called multicollinearity. Multicollinearity is basically 2 predictors that say the same thing. 2 predictors that say the same thing, and I'll put kind of say in quotes because it's not really saying anything, but I think you understand that, kind of contribute to the same thing, that say the same thing. Okay. So that's multicollinearity, and usually you have to find which variables are perfectly correlated in that case, or if you have something that's extremely highly correlated, you might think twice about including them. Exactly. So then you would want to exclude 1, right? So 2 predictors that say the same thing. Remove 1 of the redundant variables. From the model. Good. Okay. Kind of the opposite of that is if you have some variable that should be in your model but isn't, then that's what we call a confounding variable, right? So a variable that's missing, okay, that you haven't accounted for in your model, but is kind of hiding out in the background, and it is affecting it, the relationship. So the opposite of multicollinearity is a confounding variable. Right, which is really when an important variable is not included in the model. Oops. Okay. But it's affecting the relationship, right? So it's possible that that variable is in your data set, but usually it's not included in your data set, right? It hasn't been measured. So then you would try to find a variable that could stand in for that variable, right? And so what if the temperature outside is affecting a relationship, but you didn't record the temperature outside? Obviously, this is a bad example because you could go back and you could find the temperature. But what could we substitute? We could put in, we've probably got the date, right? So then I could use the date as a substitute for that missing variable that is affecting the relationship, right? So there's things that we can do, right? Even if you haven't collected that information explicitly, right? Maybe there's a variable that can kind of stand in its place. So an important variable is not included in the model, but affects the relationship. Okay. So yeah, so you could, if you can generate it, right, then you should. But you can also try to find something as a substitute, right? And so usually this variable is not included in the data, because if it were, you would just include it in your model and it would be fine, right? And so that's usually not the case. So usually this variable is not in the data, right? So we would try to find a substitute, right? So we would try to track down that data, but that's not likely, right? So we try to find a substitute for this variable in our data. Okay. Okay, so slightly different from multicollinearity is what if I think that two variables are going to change together, right? That's not unheard of, right? What if I have age in my model and I also have salary in my model? It's not too crazy to think that as I age, my salary is also going to increase, right? And so then what we have is this interaction effect, right? I've got this relationship between two variables that I want to capture. Okay. And so if we suspect that two or more, there could be more than two, but let's just focus on two. So if we suspect two or more, I'll put in brackets here. Two or more predictors might be dependent on each other, We can include the interaction effect. We can include an interaction in our model. What's interesting is it is actually multiplying the two predictors together. Okay, and so our model becomes y hat is B0, and I think we've been using hats, right? Plus B1 hat x1 plus B2 B2 hat x2 plus B3 hat x1 x2. Okay, so notice how they each have a coefficient, right? But also this is the interaction effect. So the interaction effect, whereas this is the main effect, right? With each predictor individually, those are the main effects. And then if we have this interaction here, which we literally multiply the two together, then that's the interaction effect. Okay? And then the coefficient is going to tell us how things change as these two are being multiplied together. Okay, a little bit harder to interpret, right? It's still possible, but it's a little bit harder. All right. Luckily, because I'm almost completely out of time, but here's where we go into residual analysis, right? So regression diagnostics. So we use regression diagnostics which is that a residual analysis, which we actually spent a fair amount of time working on at the beginning of the term. Residual analysis from the beginning of term. So we use regression diagnostics, not so much to check our actual, how our model does, but instead for anomaly detection. So we use regression diagnostics more for anomaly. So strange values, anomaly, strange values detection. Okay, picking up on those weird values, right? So we use those residuals to figure out, okay, do I have any data entry errors? Was the machine broken that day? That kind of thing, to clean up our data. Okay, and so the last thing I want to say, and I'll include it in the notes here, is what if we have a nonlinear relationship, right? We have a couple of different options. I could add, as well as, for example, x2 here, I could have x2 squared, right? Instead of x1 times x2, it's not too strange to think that maybe I have an x2 times x2 relationship, right? And so then you could add a polynomial term, or you could do a series of polynomials, which are called splines, or you could, because then you have to specify where those knots are, or you could have it automatically generate those knots, and that's the general additive model. And with that, I'm out of time. And so if you have any questions, let me know. Otherwise, happy St. Patrick's Day, and I hope you have a great weekend, and I'll see you next week. Thanks, guys. Stop this.